In this demonstration, we're going to look at the effect of condenser and steam generator pressure on the thermal efficiency of a Rankine cycle. So we're starting off here with just the default conditions, but because the default conditions don't have any superheat at the turbine inlet here, I'm going to put 200 degrees of superheat in here just to get a little more realistic conditions. So now we have a superheated inlet to the turbine, and this is our turbine process. So I want to take a screenshot of these operating conditions so that we can compare as we make a few other changes to these baseline operating conditions. So we'll just take a quick screenshot of the operating conditions. So we'll save these operating conditions and compare with them later. So the first thing I'm going to change is I'm going to reduce the condenser pressure from 10 kPa to 4 kPa. That happens to be the lowest pressure that this simulator can handle. So I reduce that pressure to 4. So this line of constant pressure here has dropped down to 4 kPa. And of course, because it's inside the liquid vapor region, that means the temperature in the condenser has also dropped. So if we come up here and we compare our new thermal efficiency with our old one, we see that the thermal efficiency used to be 40.36. Dropping that condenser pressure has increased that quite substantially, up to 42.63. So that's a very significant increase in thermal efficiency. Now, even though this is not a Carnot cycle, remember the expression for thermal efficiency of a Carnot cycle, 1 minus Tc over Th. Now, even though this is not a Carnot cycle, that equation still tells us the two most important parameters we can control even in this cycle. They will also have a big impact on the efficiency of this cycle. So by lowering the condenser pressure, we have lowered Tc. So this temperature down here is now lower than it used to be. So 1 minus Tc over Th, Tc has got smaller, so the efficiency has increased. So I'm going to put this back to 10 just so we're comparing to those baseline conditions again. This time we're going to go to the steam generator and we're going to increase the pressure there. So I'm going to go from 100 bar up to 120 bar. And in the TS diagram, that will have shifted this line up, so also it will be happening at higher temperatures. So now let's take a look at what happens. So now let's compare with our older conditions. So our thermal efficiency for our baseline conditions was 40.36%. Now it's 41.16%. So increasing the steam generator pressure has increased the temperature at which we're adding heat, and that is increasing the thermal efficiency of the cycle. So anything we can do to decrease Tc or increase Th helps the thermal efficiency. And in a Rankine cycle, we decrease Tc by decreasing the condenser pressure, and we increase Th by increasing the steam generator pressure. So we want those two pressures as far apart as we can in a Rankine cycle to increase the efficiency. So that's why in a practical cycle, the condenser is operating down here at these relatively low pressures. Remember, atmospheric pressure is about 100 kPa, and this condenser is only 10% of that. So if we were to increase the pressure in the condenser to atmospheric, so 100 kPa, let's see what it does to the efficiency. So notice over here it's 41.16. I'll hit enter here so that gets calculated, and it drops dramatically down to 34.19. So we would never have the condenser operating at that high a pressure because the temperature is high, and that decreases the efficiency of the cycle.